All right, everyone, welcome to class. Sorry I could not be here today. I have some appointments and things to take care of. Hopefully, you guys can get through this without me. It's a pretty straightforward lesson, so I'm pretty confident that you will be okay. I will go through the slides with you through this video, and then you should be able to go through the practice, and it should be a very straightforward lesson. The goal for today is talk about differential rate laws, and that really is the main goal. If you can figure out how to write a differential rate law by the end of today, you will be good to go. All right, so we will go through these slides together. Today's rate laws. The clock demo we're going to do on Thursday. So also make sure on Thursday that you guys come ready to be excited about stuff. All right, move over. Okay. So here is the first thing we're going to look at today. So looking at concentration over time, we talked last time about how reactants decrease in concentration over time. But we also mentioned that the rate is really dependent on when you measure it exactly, right? So initially we had 0.9 molar, and our rate is 5.4 times 10 to the negative 4. And this is molarity per seconds, essentially. And then when we went down to 0.45, the rate is now lower since our reactant here, right here, has been being used up. So the question to think about, though, is how does the rate relate to that concentration change, okay? Because there's this 2 here, but does that 2 have any significance in what's happening in the relationship between the rate and the concentration? So that's kind of the question of the day, is how do we figure out how the concentration is related to the rate? So here's the thing, when you address concentrations, it does not always go the same way. It really depends on the reaction you're doing, and there are different ways that the rate can respond to a change in the concentration of a reactant. So we call it the order of the reactant. The order of reactants is basically their effect on the rate. So do they affect it as the same as they're affected, or do they affect it more or less or negatively? That's the order of that reactant. And the key thing for today that I need to drill into your brains is that orders are not based on the stoichiometry of the reaction. And what that means is, in our slide before, when it said that there was 2 N2O5s per reaction, that does not mean we have an order of 2. It really depends on the data you're getting in the lab. So we'll see how that goes throughout the rest of this. But here are the different options of the main orders you'll need to know: 0, 1st, and 2nd. So basically, if a reactant is 0 order and I double that reaction, nothing happens to my rate. So I would put double of that thing in and the rate would just be the same. And so here's an example. If we tripled the rate, it would stay the same as well. So that's 0 order. We also have 1st order reactions. In 1st order reactions, if I were to double, this is hard to write. If I were to double, the rate would also be doubled. That would be the 1st order. It affects it in a factor of 1. And so if you tripled it, the rate would be tripled, and et cetera, and et cetera. Now keep in mind, I'm not just adding some, I am doing this in multiples. So this will always be in multiples. 2nd order is interesting. 2nd order has a squared effect. So if I were to times it by 2, the rate would be times by 4. Or if I times it by 3, the rate is times 9. It's a squared effect. So it's not like it's double the effect, it's the effect squared. So sometimes it gets confusing when people look at the times 2 example, which is why my example over here is times 3. But it's a squared effect on the rate. So if I doubled that concentration, the rate used to be 1 molarity per second, now it's 4 molarities per second, stuff like that. So there are also such things as half orders, which do weird half things and can do square roots and things. If I had a half order reactant, if I doubled it, it'd be weird. It's just weird. They don't come up very often on the test. Negative orders affect it in a negative way. So if I doubled it, the rate would go down by half, which is not the usual thing to happen. So really the ones you need to know are these 3 up here. All right. So if we go back to this and we look at what's happening here, from here to here, I am basically decreasing my concentration by half. And if we look at the rate, it is also decreased by half. So I have a half factor here and a half factor here, meaning that this is first order. Wow, I hate this pen. Might have to just change it to something else. All right, it is first order in respect to N2O5. So as you can see, looking at it, looking at the effect and looking at the change in concentration, we can tell kind of what's going on and how the rate will be affected. So if it's first ordered N2O5 and I, instead of halving it, I doubled it, it would increase the rate by the same amount. Okay, so now when we have more than one reactant, things get confusing because in the last example, we only had the one reactant. It was really clear to see. But sometimes different reactants are at play and they might have different orders from each other. So a rate law is the way to see the order of each reactant and kind of how it's affecting the overall rate. So there's two types of rate laws. There's the regular rate law, which is like the differential rate law right here. This is the one that we're doing today. There's also an integrated rate law, which is, if you're into calculus, you integrate the other rate law and you get a new rate law. That one's interesting because it's dependent on time, and it's really useful for some things. We'll come to that one later. But the key thing that we need to talk about is that you have to do the reaction to get the rate law. You cannot look at the reaction's equation and decide what that rate law is going to be. It is experimentally done. So only experimentation can do this. And once again, I'm going to put this out there. We cannot base it on the coefficients of that reaction. All right, let's get into it. This is what rate laws look like. If I say write the general form of the rate law, this is what it's going to look like. So rate is obviously R. The rate constant here is K, and that's different for each reaction. That's also experimentally found. This has different units depending on the lab you're doing, so units are a key piece of K, and we'll go over that later. Reactants 1 and 2 are A and B, and the brackets mean concentration. I gave up on the pen. I'm doing this with my finger. Okay, so the bracket means a concentration, and we're going to measure that in molarity. You could also see it as moles over liters, because that's the same thing, right? Sometimes you'll see it as mole times liters -1. Those are all different ways you could see that concentration. And then the X and the Y are exponents that are telling you the order of each reactant. So if it's first order, that effect is equivalent. If it's second order, it's squared. If it were, say, third order, it would be to the third power. So the orders will become these exponents, all right? So you'll notice that there are no products in the reaction. We are only going to include reactants. And the reason why you're going to be able to do that is because we are going to do this method where we use initial rates only. At the very beginning of the reaction, we're assuming we only have reactants and no products have been made yet. So we don't have to worry about their effect on the rate at the very, very beginning. And so that kind of area at the very beginning is what we're going to use to tell what the rate law of each reactant is. We're going to just ignore the products because we're going to be doing it at the beginning when there's only the reactants in the reaction. So this is called the initial rate method. And it is what we're going to be learning today. Basically, all that means is when you do the reaction, you measure how fast it goes at the beginning and then you stop, and then you don't care how fast the rest of the reaction goes. So for example, if I go all the way back here, I would really only look at the rate in like this section and be like, how fast is that? And then what I'll do is do a different experiment with a different concentration of this at the beginning and then compare those two. So rather than comparing throughout the reaction, we'll compare two different trials just at the very beginning. So that's what we're going to see in the data that we're going to be looking at today. Here's the first example. So we have this reaction, so it's NH4 plus NO2 minus, making N2 and H2O. This is a very stereotypical table for rate laws that you're going to see. There will be multiple trials. There will be each reactant's concentration and then the initial rate. And sometimes that rate is measuring the amount of products made. Sometimes it's measuring the amount of reactants used up. Like we saw last time, you can measure rate of reaction in a lot of different ways. It doesn't really matter what they pick here. What we're looking at is the relative change, so it does not really matter what's going on there. So we're going to do these three things. We're going to write the basic rate law expression. We're going to find the orders of each reactant, and then we're going to calculate the rate constant. And it's going to be pretty straightforward. So basic rate law expression, here we go. Rate equals, we put a rate constant K, we don't know what it is yet. We put brackets and then we put the first reactant close brackets, to some power, we don't know that yet. Second one, NO2 minus. Beautiful, we did number one. That's a basic rate law expression. So in a basic rate law expression, all you're gonna do is plug in the reactants into the rate law and leave the K, leave the X, leave the Y. We'll find those out in the next part. Number two, find the orders of each reactant. So what we're gonna do now is we're gonna look up at the data we're given, okay? Because this is a data-driven type thing. You're gonna find two trials where only one thing changes. Sorry for my handwriting, it's a T, changes. So we're gonna look at the first two experiments, experiment 1 and experiment 2. As you can see, NH4 is staying the same, and NO2 has gone up times 2. It's doubled. So now what you do is you go look at the rate. What happened to the rate? It has also doubled. So that does not mean we are second order for NO2. Because the two effects are the same, we are first order for NO2. So the first thing we decided is that this Y is the number 1. It's first order because the effects are exactly the same. All right, now let's look at a different color. Let's go look at, we're trying to find NH4. So we're gonna pick two trials where NH4 changes and NO2 stays the same. So we're gonna do trials 2 and 3 this time. This one and this one. As you can see, this is constant. This has gone up again times 2. They often do times 2 just because it's simple to see. And if we look over here, okay, 2.7 times that by 2, that's also first order. So we also have a 1 right here. This is really how you problem solve this. It doesn't really get too much more complicated. Sometimes it's harder to see what the actual multiple is, especially in the rate, because those numbers are harder to see. If you ever are confused, all you gotta do is take the bigger one and divide by the smaller one, and then it'll give you the number. So if I wasn't sure, I could do 5.4 times 10 to the negative 7 over 2.7 times 10 to the negative 7, do that in my calculator, and I could get that 2 value, and it would be the same. So you can always divide them out to get the number, but most of the time they're going to pick stuff that's pretty easy to see, especially in the concentrations. Keeping in mind, this section that's right here, they chose what initial concentrations to use, so it would make sense to choose ones that are easy to see and easy to follow. So now I can write the rate law. So the rate law would be rate equals K NH4 plus NO2 minus. That's the rate law. You'll notice there's no exponents now because if you plug in 1 for x and y, so anything to the 1 power is just itself, so this would be what I call the rate law. Now, this is the rate law, and a lot of times they'll let you leave it just like this, and then the next step will be to find K. So to find K, all we're going to do is, let me put this in blue as another step. You're going to plug in one trial and solve for K. Pretty straightforward. So this is our rate law. Let's go back up. Whoa. I want all of it. Okay, I want to, great. Great. We're going to just move that up there. Okay, we're going to pick, say, let's do the second trial only because there's a lot of 0.1s and 0.01s, and that's going to make things pretty easy for us. So I'm going to do NH4. I'm going to just, I guess we'll move this down. Move this here. Here's my rate law. So we're going to do the rate, which is 2.7 times 10 to the negative 7. It does not matter which trial you pick. Molarity per second equal to K, and then the first one is 0.1, the second one is 0.01. And then you would just solve for K, keeping in mind that these are all molarities. All right, if I can get all the way up here. This is being annoying. Okay, so now here is my thing, right? All I'm going to do is do this math. So let's just plug it in a calculator, and K will be equal to, it'll be 2.7 times 10 to the negative 7 divided by 0.1 and 0.01. I get 2.7 times 10 to the negative 4.
Hey, Thomas is here.
Hey, I'm in the middle of a video.
You what?
I'm recording. Talk to you in a sec. All right. So that's the K value. And now almost always K will be associated with units because the units are different depending on what the orders here are, right? So if we look units only, we have molarity per second equals K times molarity times molarity. And if we do this math, we divide by molarity squared on each side, what we're going to get over here is, let's see, these cancel. So then we'll have molarity over seconds over molarity squared. So this is going to cancel out with one of these. So we'll get 1 over seconds over molarity, which is basically just molarity over seconds. Now I'm doubting my math. Why is that? So this should be the same as molarity over seconds times 1 over molarity squared. Oh, that's why. So this cancels, and this becomes 1 over molarity seconds. So this would be 1 over molarity times seconds. Okay? So that's one version of a rate law units. There's other ones depending on the orders. So let's go back to what we were trying to do here. All right, we read the basic rate law expression that was here. Finding the orders of each reactant we did using this method. And then calculate the rate constant. All we did was take one of the 3 experiments, plug into the rate constant rate law we got, and we got the K value. So if you wanted to, you could then rewrite the whole rate law using our new K value. And I could do that like here with, well, now that I have space. I could say that the rate is equal to 2.7 times 10 to the negative 4 concentration of NH4 plus concentration of NO2 minus. So this is the complete full rate law with the K value. Oh, this should be 1 over m seconds. There you go. This would be the complete rate law. Now, oftentimes, though, in the AP test, when they ask you to write a rate law, they don't need you to find K, but this would be with K included, and that would be for this reaction based on the experiments given. All right, so take that in. We're going to do one more example, but I'm making a different video because this video has already gotten pretty long. And we're going to do the same thing, but a little bit more complicated with 3 different reactants instead.